We have seen how to go from any continuous distribution to uniform 0, 1. In this video, we are going to see its converse, a very strong version of the converse, which says how to start with a uniform 0, 1 random variable, and from that you can generate a random variable following any arbitrary distribution. You do not even need the continuity assumption. Suppose that the distribution that we want to arrive at is specified by its CDF, capital Fx. Then we shall first define a kind of inverse of this capital Fx and call it F minus 0, 1 to R, open 0, 1 to R. It is defined as, for any y in open 0, 1, F minus of y is defined as, consider all t such that ft is greater than or equal to y, take the infimum of that. Pictorially, suppose this is your capital F graph, non-decreasing. I take some y, then I just draw the horizontal line. In this example, this value will be f minus of y. However, if this graph looks like this with a flat region and your y happens to be exactly at that flat value, in that case you will consider all those ft's such that it is greater than or equal to y, so it is this part, and the infimum will force you to seek the leftmost point of that, so this will be your f minus y. If the graph of fx has a discontinuity, so there is a gap, and your y happens to be a value that is inside the gap, in that case you will again consider all ft greater than or equal to y, so in this case this part, you will go to the left hand point, the leftmost point, so your f minus y will be this particular value of x. Now let me assure you that this quantity is always well defined. For this I need to show that this set is non-empty and bounded from below. It is non-empty because since y lies strictly between 0 and 1, you can always take a value between y and 1. And since a distribution function must go to 1 as x goes to infinity, somewhere or other it must cross that value. So that particular value is bound to be inside this set. So this set is always non-empty. To show it is bounded from below, you again observe that y lies strictly between 0 and 1, so there is some value which is between 0 and 1, and you draw a line like this, because f will converge to minus infinity as you go towards the left. Somewhere or other it will fall below that line. So that point must be a lower bound for this set, because if you take some point even to its left, it will be less than even this line. So how can it be more than y? So this is a non-empty set and it is bounded from below, so its infimum exists, and that is what we have defined like this. Here is an important theorem that we are going to use. Fx is any CDF, then f of f minus y is always greater than or equal to y. The proof comes from the right continuity of f. Let's understand the proof pictorially. Suppose that this is the graph of fx. Now if you take y, here in that case f minus y will be here, and you can immediately see that f of f minus y is equal to y. So you get equality. If you take it here, in that case also the same argument holds, because f of f minus y will be the leftmost point, and again you see the value there is y. So as long as you are having a y through some level where f is continuous, then you just get equality. That's trivial. Now if your y happens to land here, which passes right through the gap, in that case that is your y, and this is your f minus y. And you can see, because which is right continuous, so the dot is attached to the right end point. So the value f of f minus y is height of this point, which is above y. Of course, you can write it down using inequalities, but this is the basic idea. The second part is, if you take any x in R and any y in open 0, 1, then these two inequalities are actually equivalent. Pictorially, suppose here is my capital Fx graph and I have taken some y and the corresponding f minus y. Now, whenever you take x to the right of this, the corresponding fx will be above y. Similarly, whenever you take any x such that fx is above y, that x must be to the right of f minus y. The proof is very simple. Let's do this side first. So we start with this. Now we know that f, capital F being a CDF, is a non-decreasing function. So I can apply f to both sides without disrupting the inequality. I know this is greater than or equal to y. So I have y less than or equal to fx. That's exactly what I wanted to show. Conversely, start with y less than or equal to fx, which means x is in this particular set because fx is greater than or equal to y. Since x is in this set, x must be greater than or equal to infimum of this set, and infimum of this set is precisely f minus y by definition. So we have shown x greater than or equal to f minus y. So we have proved the theorem. Now for the important theorem, that is the main theorem of this video. I start with any CDF and I start with some u which has uniform 0-1 distribution. Then f minus u has CDF fx. The proof is very simple, just one line, but let's take some time to understand why it is interesting. I started with just a uniform 0-1 random variable and I took any distribution. Taking any CDF means taking any distribution, and I could actually manufacture. This is a random variable. I manufactured this random variable which has that required CDF. So this actually proves half of the fundamental theorem of probability. Given any CDF, there is a random variable following that CDF. We actually manufactured that random variable. I say it is half of the proof because I still used something. I used a uniform 0-1 random variable. Once I prove that there is something called uniform 0-1 random variable, such a thing actually exists in the world, then together with that it will prove that for every CDF there is a random variable having that as the CDF. Now for the proof of this fact, this theorem, I give it a name. I want to show that this has CDF this. In other words, I want to show that for any real number a, probability y less than or equal to a is capital F a. Now probability y less than or equal to a means probability f minus u less than or equal to a because y is f minus u. Now the last theorem already gave us a way of writing this in a way such that f minus basically comes on this side. So we get that this is probability u less than or equal to fa because the last theorem said that this if and only if that. Now fa is a number between 0 and 1. So this uniform 0-1 random variable is less than or equal to a number between 0 and 1. That is just equal to fa. And that completes the proof. Very simple proof. Now apart from being half of the proof of the fundamental theorem of probability, this is of great application in computer programming because this is how any computer system generates random numbers from any given distribution. Inside every computer system like R or Python or MATLAB, it has some way of generating random numbers from uniform 0-1. Then they apply this technique to generate random numbers from any specified distribution. We have already given a few properties of f minus. There are many other properties. One of them is that f minus is a non-decreasing function. The proof is pretty straightforward. Try to do it.